Having done left inverses and right inverses, let's finish with two-sided inverses. So the result we're going to prove is that a function is invertible if and only if it's a bijection. And of course, because invertible means two-sided invertible, we're going to be able to use the things we already proved about left and right inverses. So again, one direction of this will be nice and easy. Let's suppose that we have a function f from a set x to a set y, have a two-sided inverse g. So g is a function from y to x, and g composed with f is the identity on x, and f composed with g is the identity on y. Well, then, what can we say in particular? G is a left inverse to f. So by the thing we proved 2 slides ago, f is injective. And equally, g is a right inverse. So if it's a right inverse, then by the thing on the previous slide, f is surjective. So putting those together, f is a bijection. Okay, now the difficult direction, or the harder direction at least, is to show that if f is a bijection, then it must be invertible. So why does that not just follow straight away? Let's think about this. Why doesn't that follow just immediately from the 2 results we proved about left and right inverses? So now we'll suppose that f is a bijection. Okay, bijective means injective and surjective. So f is injective. If it's injective, then we proved that it must have a left inverse, g. And f is surjective, so it's got to have a right inverse. Okay, but here's the problem. If you want a function to be invertible, to have a two-sided inverse, then the same thing must be both a left and a right inverse to f. And at the moment, we don't know this. We know that f has a left inverse, and we know that f has a right inverse. Let's call it h. But we've got no reason at the moment to suppose that g and h must be equal. So we need to show that actually those 2 things are the same. So I claim that actually they must always be the same. Let's do the calculation. So there's just a silly trick you can do here. So we let little y be in big Y, then, well, actually we don't even need to do this with elements. So actually I realize I can do this slightly easier. Let's just think about h. Well, h is equal to the identity on y composed with h. H goes from the identity on x composed with h, because h goes from x to y, if f goes from y to x. So let's put this in. F is going to be a function from x to y. And then h and g will be functions from y to x. So I can compose on the left with the identity, and of course I don't change anything when I do that. But g is supposed to be a left inverse to f. So that means g composed with f should be the identity on x. So I can substitute g composed with f with the identity on x. So this is because g composed with f is the identity on x. Okay, that should have been a compose symbol. That's better. Okay, function composition is associative. So I could rewrite this as g composed with f composed with h. So this is by associativity. Okay, now h was supposed to be a right inverse to f. So f composed with h is the identity on y. And of course, composing with the identity doesn't change anything. So G composed with the identity is just G again. Okay, follow that chain of equalities. You've shown that H is equal to G, and therefore G, or H, is a two-sided inverse to F. Okay, so we're done. And actually what this argument shows is that if f is invertible, then it's got one and only one inverse function, because if you had two inverses, so let's say g and h were two-sided inverses to f, then g would be a left inverse and h would be a right inverse. So you could just trail through this argument that we did at the bottom, and that would show that these two inverse functions for f, these two-sided inverses, would have to be equal. So we have some notation for the inverse of an invertible function. If a function f is invertible, it's only got one inverse function, and we use this notation, f to the power minus 1, for the inverse of the function f. So finally, let's just look at one useful thing that we can say about invertible functions, so functions which have two-sided inverses. And that is that if you have the composition of two invertible functions, then that is also invertible. So in the language of this theorem, if you've got a function f from x to y and g from y to z are invertible, then you can form the composition g composed with f, and in fact that is invertible. So it's got a two-sided inverse. So proving something has a two-sided inverse is usually straightforward. If you know what that two-sided inverse is going to be, you just check that the composition is the appropriate identity. And here, so what do we want to do? Well, we want to show that g composed with f has a two-sided inverse, which is f inverse composed with g inverse. So to check that's true, let's just look at g composed with f composed with f inverse composed with g inverse. Okay, what's going on? We can use associativity to re-bracket this however we like. So I'm going to re-bracket it like this. So this is by associativity, SOC for short. Okay, f composed with f inverse is the identity on y. Of course, g composed with the identity is just g again. So this is g composed with g inverse. And of course, this is the identity. Where is it the identity? It is the identity on z. Okay. So we've shown that one of these compositions is the identity. So similarly, if you do the composition the other way around, you find that you get the identity on x. And so f inverse composed with g inverse really is a two-sided inverse to g composed with f. Alright, so the important thing to remember here is that you are composing the inverses the opposite way round, right? The inverse of g composed with f was f inverse composed with g inverse, so the opposite way round to the original composition. There's a easy way to remember this, which is just to think about, at least pre-pandemic, what people used to do in the mornings. When you woke up in the morning, you get out of bed, you put your shoes on, you put your socks on, and then you put your shoes on, and you have to do it in that order. It doesn't make sense to do it the other way around. And then at the end of the day, when you wish to invert this procedure, you can't take your socks off and then take your shoes off. It's usually impossible to do that. So you have to do it the opposite way around. You have to take your shoes off first and then your socks off. That's why the inverse of g composed with f is f inverse composed with g inverse, the composition the other way around.